Yes, Chemistry Paper 1, May 2019. Question number 1.1. Sodium fluoride contains sodium ions Na plus and F minus ions. They've both got the same electronic configuration. So how's that come about? Well, sodium Na has got 11 protons and 11 electrons. Fluorine's got 9 protons and 9 electrons. So Na plus has lost 1, it's got 10 electrons, and F minus has gained 1, it's gone from 9 to 10. They've both got 10 electrons. They've got the same electronic configuration. So I put that here, both atoms have the same number of electrons and the same number of shells, so the same amount of shielding. Normally you'd put that in. The reason I put it in brackets is it's actually not needed. Brackets means it's not wrong to put it, it's correct chemistry, but it's not going to get you any marks. And the reason in this case it's not going to get you any marks is because they've already said that they've got the same electronic configuration, so I'm really repeating what's in the question. However, this is important. Fluorine has less protons than sodium, so it's got an atomic number of 9. Now when it's gained F minus, it's gained an electron and got 10 electrons, but the number of protons hasn't changed. And similarly, Na has got a proton number of 11. Well, when it's lost an electron and gone down to 10 electrons, the number of protons is still 11. So Na has got 11 protons and F has got 9 protons. That's unchanged by the plus and the minus ions. So fluorine has got 2 less protons. It's got 9 protons rather than sodium's 11. Good to put the 2 in to actually name it, but again, you don't get any marks. It's got less protons than sodium, so it's got a lower nuclear charge, and therefore it's got weaker attraction. Again, good practice to put outer electrons, because it's the outer electrons that determine the size of it, and so less attraction for the outer electrons having 2 less protons than sodium. To explain in terms of structure and bonding why the melting point of sodium fluoride is high. Well, look, you've got ions. The reason you've got ions is sodium wants to lose 1 electron to fill up its outer shell, and fluorine wants to gain 1 electron to fill up its outer shell. Sodium's in group 1, fluorine's in group 7. So the sodium atom donates an electron to the fluorine atom and becomes an Na plus ion, and the fluorine becomes an F minus ion. And those attract very strongly with something called an ionic bond, sometimes called electrostatic attraction. So because they're oppositely charged ions, they attract very strongly, ionic bonding or electrostatic attraction. They're also held in a regular ionic lattice. That's a good thing to put. It doesn't actually in this case get you any marks, but it's a good thing to put. It means that it's in a stable, regular ionic lattice. Anyway, a large amount of energy is required to break these stronger ionic bonds. That's important because that then relates to the melting point and why you need a high melting point, a large amount of energy to be able to break that ionic lattice and turn the solid into a liquid. Name the type of bond formed when HF reacts with H+. Well, what is a H+? A hydrogen atom, before it's gained a plus charge, has got a proton number of 1. It's got 1 proton and 1 electron. Now it's become 1+. It hasn't got any electrons at all. It's just a proton. That's all it is. So how can it form any kind of bond if it's got no electrons? Well, it can form a special kind of covalent bond called a coordinate bond. And normally a covalent bond is where one atom puts 1 electron in and the other atom puts an electron in each, and they've got a shared pair of electrons between them, both wanting to gain electrons. But this H+ has got none to put in there. So what actually happens is it's a covalent bond that's formed when both electrons have come from one of the atoms. So one of the atoms forming the covalent bond has put both electrons in rather than each atom putting 1 in each. And that's come from the F, because it's the F that's bonded to the H's. So the F has put both electrons in to this covalent bond, and it's called a special kind of covalent bond. It's called a dative or coordinate bond, whichever you want to put, whichever you can remember. So what I've got here, SPF minus 6, I've got to do the shape and the name of the shape, and similar for H2F+. So let's do SPF6 minus. If you find SB, it's in group 5 of the periodic table. It's gained an electron, so if it's in 5 of the periodic table, group 5 of the periodic table, it's got 5 electrons in its outer shell, gained 1, it's got 6 electrons in its outer shell, it's bonding 6F, so it's got 6 bonding pairs. I always put the minus in brackets. The brackets in this case doesn't denote concentration as it often does. In this case, it just means somewhere, somehow, there's a minus charge on here. It's almost like a wrapper around this to say somewhere there's a minus charge in this. It's gained a minus, it's gained an electron. So it's got 6 electrons in the outer shell, 6 bonding pairs, all repel equally, octahedral shape. If it was asking for the bond angle, it would be bond angle 90. H2F plus, so what's the F got? Well, that's F is in group 7. If it's a plus, it's lost an electron, so it's not got 7 in its outer shell now, it's got 6 in its outer shell. If it's got 6 electrons in its outer shell, 2 are involved in bonding pairs, it puts an electron in each of these covalent bonds, so 2 bonding pairs. It had 6 in its outer shell, 2 bonding pairs, it's got 4 left over, it's got 2 lone pairs. So that's how we draw it. Again, the plus charge, I put square brackets around to say that there's a plus charge somewhere on this molecule. How are they going to repel? Well, the 2 bonding pairs repel most to the greatest extent, and then the bonding pair, so the 2 lone pairs repel greatly to the greatest extent. The lone pair to bonding pair repels to the next greatest extent, and then to the least greatest extent the 2 bonding pairs repel. So these 2 bonding pairs get pushed closer together. Normally, if it were 1, 2, 3, 4, a tetrahedral shape, it would be a bond angle of 109.5. Every time we replace a lone pair with a bonding pair, the bond angle goes down by 2.5. So if it's 1 lone pair and 3 bonding pairs, it comes down from 109.5 down to 107. 2 lone pairs comes down by 2.5 again, down to 104.5. And you actually, although the lone pairs influence the shape, you actually don't use those to name the shape. You only name the shape according to what you see, i.e. the atoms, and we can see 3 atoms here, and it's in a bent shape or a V shape, whichever you prefer. Hydrogen fluoride with ethine, so that's C2H2, we've got the equation here with 2HF, makes this chemical here. It's called 1,1-difluoroethane, and the enthalpy change is minus 179 for this. So mean bond enthalpy, use the data in here to determine the bond enthalpy of a CF. So it's these 2 that we don't know here. So what we do is we do the bond enthalpy, which is minus 179, equals the bond enthalpy of the reactants, that's anything on the left, minus the bond enthalpy of the products, anything on the right. So what have I got? I've got 2 C2H bonds on the left in my reactants, so minus 179 is 2 C2H bond, 1 C to C, that's a triple bond, plus 2 HFs, take away, so subtract the bond enthalpy of the products, say take away 4 C2H bonds, I've got 4 of those, 1, 2, 3, 4, and 2, take away again, because it's a product, take away 2 C to F bonds. So let's put the numbers in then now. So if you put the numbers in, a C2H bond is a 412 plus. They're all plus values because they all involve endothermic reactions, putting energy in to break the bonds. So they're all always plus values for the mean bond enthalpy. Plus 837, so that's the energy required to break a carbon-to-carbon triple bond. 2 HFs are 2 562s. Take away, subtract 348 for a carbon-to-carbon. So we've got a carbon-to-carbon bond. I should have put that in there really. I've missed the carbon-to-carbon bond in this top line here. But there's minus 348 for a carbon-to-carbon bond to break that one in there. 4 412s. 4 carbon to hydrogens, and then minus the 2 carbon to fluorine bonds that we don't know of. That's what we're trying to find out. Put all the numbers in, take them across to the other side. So minus 968, when you take all these numbers across to the other side, equals minus 2 times the carbon to fluorine bonds. Reverse the sign on both sides. 968 is twice the enthalpy required to break the carbon to fluorine bond. So divide by 2, 484. Got to be a plus value, as I say, because bond enthalpies always require energy. The endothermic reactions with plus delta H values require energy to break the bond.